In this video, I'm going to be discussing a very useful relationship involving the sum of sinusoids. Often in electronics, particularly with AC steady-state analysis, we are exciting networks with sinusoids. And also in Fourier analysis, we use sinusoids. So it naturally arises as to what happens when you simultaneously excite a network using multiple sinusoids of the same frequency and injected at different points in the network. So the relationship I'm going to be investigating is this one, is where we have the sum of two sinusoids. We have a cosine with amplitude A, a sine with amplitude B of the same frequency. That's important. They have to be of the same frequency. And then the sum of these two ends up being a sinusoid of a modified amplitude, where the amplitude is the square root of the sum of the squares of the individual amplitudes, and it's phase shifted by an angle phi, where phi is the arctangent of the ratio of the two amplitudes of the sinusoids. And the way we can remember this is if you write as A cosine theta plus B sine theta, the arctangent is B over A, the amplitude of the sine over the cosine. Remember, tangent is sine over cosine, so the arctangent of phi would just be B over A. Now, in proving this, we're going to be using complex variables, in particular the Euler identity, which is probably the most fundamental or the most famous and important equation in mathematics. In complex variables, in complex numbers, we have an exponential raised to a pure imaginary number, that e to the I phi. Remember, I in complex numbers is the square root of -1, a pure imaginary number. So e to the I phi is cosine phi plus I times the sine of phi. We have a real part and an imaginary part. Now, another way we can write this is if we have a complex number, z, call it, which is a plus ib, this can be written in exponential or what we call polar form, where we have a magnitude times an exponential raised to an imaginary number at some phase angle or some angle phi. M is the magnitude, so we can also write this in using this if we multiply through by m. M e to the I phi would be m cosine phi plus I m sine phi. Well, the A part, or the real part, is m cosine phi, and the imaginary part, B, would be m times the sine of phi. Well, m, the magnitude, is the square root of the sum of the squares of the real part plus the square of the imaginary part, a squared plus b squared, and phi is the arctangent of the imaginary part to the real part, or arctangent b over a. Now, some other properties that we have, remember that if we have a complex number z, which is a plus ib, which we write in polar form as m e to the I phi, then the complex conjugate of z, and we denote complex conjugate by putting a star to the top, is a minus ib. A complex number and its conjugate are just opposite in sign on the imaginary parts, and if we write it in exponential or polar form, if z is the imaginary number, m e to the I phi, then z conjugate is m e to the minus I phi. The phase angle, or the angle, gets negated. Now also, a complex number times its conjugate gives us the magnitude of the complex number squared. So z times z conjugate is m squared, which is a squared plus b squared. The sum of the real part squared plus the imaginary part squared. If we add a conjugate to the complex number, we get twice the real part. Z plus z conjugate gives us 2a. You can see that here. If I add these two, the imaginary parts cancel and we end up with 2a. And if we subtract them, z minus its conjugate, we get twice the imaginary part times the imaginary unit, I. This is called the imaginary unit. So we can see that z minus z conjugate, the a's go out, and the two imaginary parts add. So we get 2b times I. So these properties we'll be using in proving this particular relationship. Now when we add two sinusoids of the same frequency together, we get a phase-shifted sinusoid of a modified amplitude that shifted in phase with respect to the origin. Now, to give you a feel for what's going on, in red here, I have a cosinusoid of amplitude A. The max and minimum are at A and minus A. And the sinusoid, or the sine function that we're adding to it, has amplitude B and minus B. So maximum is at B, minimum is at minus B. Now, the sine function goes through 0 at the origin and at pi and at 2 pi. This is one complete cycle. A cycle goes between 0 and 2 pi. The cosine has its maximum at 0 and minimum at pi and goes through 0 at pi over 2 and at 3 pi over 2, as I'm showing here. Now when we add these two together graphically, we pick a given theta and then add the amplitudes at a given theta. So the sum at the origin, since the sine function goes through 0, will just be the cosine value, which is in this case A. So that will be the sum. It will just be equal to A, because at 0 sine is 0, cosine is 0 is 1, so the amplitude is A. Now at 2 pi, sine again is 0 and the cosine is equal to 1, so we have the value of A at the end of the cycle. Now at pi over 2, the sine is max, the cosine is 0, so at pi over 2, the value of the sum will be the same as the cosine, and the same thing at 3 pi over 2. So those will be the value of the sum at the cardinal values here. Now at pi, sine is 0, cosine is a maximum, or maximum in the negative direction, or its minimum, so it'll have the value of minus A there. Now somewhere in between, the sum will have a maximum. That is, when we add both curves in a positive direction, it'll be positive or maximum in there someplace, and also when we add them in the negative direction, it'll have a minimum somewhere around there. Now, where the sum crosses 0 will be where the magnitudes are equal but opposite in sign. So somewhere along in here, the sum will go to 0. And same thing in here, we have a positive and a negative, and it'll go to 0 there. So we have some points here. So if we were to plot this out, what the sum will look like is that? We see that it's phase shifted. It retains a maximum and a minimum that aren't at the cardinal values that the sine and cosine were at. So we have a shift here between the peaks, and this is our phase shift phi, and the same thing if we look at the zero crossings. The zero crossing is shifted to the right a bit from the sine curve. And if with respect to the cosine curve, I'm sorry that this isn't quite right. This is not our angle phi. Our angle phi is with respect to the cosine curve. So when we plot the cosine, our cosine is here, so this will be our phase shift phi here. And the same thing here, if we look at the peak with respect to the cosine curve, this is the phase shift phi. So it's shifted to the right by angle phi from the cosine curve that we started with. So that's what it'll look like. And this is very useful identity to know, like I said, for analyzing AC steady state circuits. If you inject two signals of the same frequency at different parts of the network, those will combine in this manner and cause a phase shift in the resultant. So in electronics, our theta becomes an omega t, where omega is our radian or angular frequency and t is time. So this would be, we would be writing this as a cosine omega t plus b sine omega t equals r cosine omega t plus or minus our phase shift. So we see that if our cosine and sine are of the same frequency, the resultant will also be at the same frequency. That is, the frequency of the resultant never changes from the constituent parts. So if the sine and cosine that we're adding together are the same frequency, the resultant will be at the same frequency, but phase shifted. Now, let's go ahead and prove this using complex variables. Now, let's form the sum A cosine theta plus B sine theta using complex numbers. I'm using Euler's identity, as I showed you previously here, for cosine theta, written in exponential form, is e to the I theta plus e to the minus I theta over 2, and then we multiply by a and expand this out. So we have a over 2 e to the I theta plus a over 2 e to the minus I theta. Same for sine. The sine is minus I times the quantity e to the I theta minus e to the minus I theta all over 2. And we multiply by b. So expanding this out, we have minus ib e to the I theta over 2 minus is a plus ib e to the minus I theta over 2. Now we're going to form the sum a cosine plus b sine. So we're adding these two. So for e to the I theta positive, we have e to the I theta over 2, e to the I theta over 2, and then we have a minus ib, and likewise plus e to the minus I theta over 2 times a plus ib. Now we notice that these two numbers are complex conjugates. Okay, and here is the trick to all this, is we will express a plus ib as a complex number in polar or exponential form. So this is, we'll call this z. Z is a plus ib, which is some magnitude r, e to the I phi at some angle. Well, r is a r squared is a squared plus b squared, and the angle phi is the arctangent of the imaginary part b over the real part a. Likewise, this, if this is z, then this is z conjugate, because we see the real part, the real parts are the same, but the imaginary parts are opposite signs. So z conjugate then is a minus ib, which is r e to the minus I phi, where r is given by this and phi is given by that. Now, let's put these in for z and z conjugate. Well, a minus ib would be r e to the minus I phi times e to the I theta over 2, and then plus a plus ib is r e to the I phi positive times e to the minus I theta all over 2. Now, when we have a product of two exponentials at the same base, or a number at the same base raised to some power, we add the powers. So we can write this now in this fashion, combining the exponents. I will put that up here. So a cosine plus b sine, that's this, is equal to, I'm going to factor out r since it's on both terms. So I've got r times, we've got e to the I, on this one it's theta minus phi. Theta minus phi, plus, then on this term, the r we pulled out, and we have e to the minus I theta. So it's e to the minus I theta, but the phi here is positive, so we have to negate it if we're putting the minus sign out front. So this is e to the minus phi. So we see this as e to the minus I theta plus, we got a minus I and a minus a, so this is plus I phi. And then all this, both terms have a 2, so that's over 2. Now we recognize this as being the exponential form for cosine. This is r times the cosine of theta minus phi. What we are looking for right here. So we see then that this is indeed true, that a cosine theta plus b sine theta is some magnitude r given by this times the cosine of theta minus phi. So this is a phase shift. Phi is the phase shift angle. And that's what we have here. Now, you can do a similar thing. Instead of writing it in terms of cosines, when we get to this part here, what we could have done is multiply the numerator and the denominator by I, and if we do that, what we end up with is, say, I over 2i over 2i, so that the i's cancel. Then when we look at our z and our z conjugate, we're multiplying these by I, which is adding pi over 2 to the angle, and then what we end up with is a form where we end up with sines. You can do that. I'm not going to do that here, but what you would end up with then is you could write this also as r times the sine of theta plus psi, and psi will be the arctangent of A over B. So theta or phi and phi are complementary angles. That is, phi plus psi equals pi over 2. They sum to pi over 2 or 90 degrees. And we can see that from the relationship there. So we can write this as two ways. We can write the sum as a cosine or a sine, but the phase shift angles will be different depending upon which of the functions you choose to write it as. You'll have a phi or a psi given by these relationships. Now, let's look at this a little bit further. So I'll write this as r sine theta plus psi, and psi equals the arctangent of A over B. Now let's look at these, the theta or the phi and the psi. So take the tangent of both sides, so we can write this as tangent phi equals B over A, and the tangent of psi is A over B. Now, these are reciprocal. We can see that. So, if we're to look at a triangle, let's look at a right triangle so we can get an understanding of this. If this is angle phi, then the tangent of phi is B over A, or opposite over adjacent. So this is opposite over adjacent. And then R is the hypotenuse, which is, by Pythagoras' theorem, R squared is A squared plus B squared. Then look at the tangent of psi is opposite over adjacent. So for psi, A is the opposite angle, so that makes this psi, and this is the right angle. So we see that phi plus psi is pi over 2 or 90 degrees. Now we can write this then as, notice that we can write the cosine of phi. The cosine of phi would be A over R, adjacent over hypotenuse. So that's A over R, and the sine of phi is opposite over hypotenuse, or B over R. How about in terms of psi? Well, A over R for psi is opposite over hypotenuse, so this would be the sine of psi. And B over R for psi is adjacent over hypotenuse, so this would be the cosine of psi. So we see we have the cofunctions for psi and phi because they are complementary angles. Now, if we divide sine phi by cosine of phi, we have the tangent of phi. But what's sine phi divided by cosine phi? That's B over R divided by A over R. The R's cancel, so we end up with B over A. And we see that right here. Remember, the tangent of phi is B over A. How about the sine of psi over the cosine of psi, which is the tangent of psi? Well, the sine of psi is A over R divided by the cosine of psi, which is B over R. So this is A over B, and this is the tangent of psi, A over B. Now, we know that these are cofunctions. That is, if the tangent of psi or phi is B over A, then A over B is the cotangent. So, or a A over B would be the cotangent of theta. So this will be the cotangent of psi, because if psi, the tangent of psi is A over B, then B over A is the cofunction of psi, and this likewise the tangent of psi will be the cotangent of phi. If phi, the tangent of phi is B over A, the reciprocal of that is a cotangent of phi. So these are our relationships. We have the cofunctions. Now we can verify that easily by looking at this. Let's look at it a little different way. If this, the cosine part is equal to this and the sine is equal to that, then they're equal to one another and they have the same magnitude. So we're going to ask, is the cosine of theta minus phi equal to the sine of theta plus psi, where theta or phi and psi are given by those relationships? Well, we can use the expansion formula for sum and difference angles on sine and cosine. The cosine of theta minus phi would be the cosine of theta times the cosine of phi plus the sine of theta times the sine of phi. And we want to know, is that equal to this? Well, the sine of theta plus psi will be the sine of theta times the cosine of psi plus the sine of psi times the cosine of theta. Okay, that's the expansion. Sine of theta plus psi is sine theta cosine psi plus sine psi cosine theta. And we want to know if these two are equal. Well, we need to look at these terms here. Cosine and sine of psi and cosine and sine of phi. Well, let's look at our triangle again. If this is R, our hypotenuse, and this is angle phi, that is B over A. The tangent of phi is B over A. And then this is our angle psi. Well, what's the cosine of phi? Well, the cosine of phi is adjacent over hypotenuse, or A over R. How about the sine of phi? Opposite over hypotenuse, or B over R. How about for the cosine of psi? Well, the cosine of psi is its adjacent side to the hypotenuse, or B over R, and the sine of psi is opposite over hypotenuse, or A over R. Okay, we'll put in for those now into our expression here, and we can see that this is A over R cosine theta plus B over R sine theta. And is that equal to, we have B over R times the sine of theta plus A over R times the cosine of theta. Let's compare. We have A over R times the cosine of theta, A over R cosine of theta on that side. B over R times the sine of theta, and B over R times the sine of theta there. So each side of the equation has the same terms. So it is equal. So we verified indeed that the cosine of theta minus phi is equal to the sine of theta plus psi when phi and sine are given by those relationships. So there we are. We have a very useful relationship that any student out there that might be taking electrical engineering, you never really see this in books. I don't know why authors never really show this. I rarely see this in any textbooks, and it's a very useful relationship, particularly when you're doing steady state AC analysis.